Section 3.2 divided differences. By using divided differences, we can find the coefficients ck for the Newton interpolating polynomials. The method of divided differences is a table construction technique. The technique, with certain modifications, can be applied for various numerical evaluations. Here we'll start with this remark. For given data points xk, yk, case moving from 0 to n, the case degree Newton interpolating polynomials are of the form. The first few cases are here: p0, p1, p2, and c0 must be y0, and the c1 can be determined to satisfy here p1x1 equals y1. So that we have here right hand side, and c0, which is y0, can be moved to left hand side and divided by x1 minus x0 to get c1 here. Now c0, c1 are known, and then c2 can be decided to satisfy that equation, p2 at x2 equal y2. So we have here this right hand side, and everything is known here. So we move this into left hand side and divide by this product. So we reach at this term. Now y2 minus y0 is same as y2 minus y1 plus y1 minus y0. Now y1 minus y0 is c1 x1 minus x0. So we have here, and we combine them, then that'll be minus c1 x2 minus x1, right? So we divide the bottom and top with x2 minus x1, then we can reach at this final term. Here we are manipulating the algebraic terms so that here we'll do this operation when we try to construct the table. We'll try to construct divided difference table, and along with such computation. So here, roughly speaking, divided difference table start with in this way. Now here x0, and for x term, okay, we start here now x term, and now f value y term, and here now that's called divided difference first order. Now x0, x1, x2, and so on. Now y value will be y0, y1, and y2. Now that is here c0, we know that. Now this one, c1 is gotten this difference divided by that difference. So here we try to put here y1 minus y0, okay, divided by x1 minus x0, that is now c1, right? Okay, and also here we do one more time here computation, that portion, okay, y2 minus y1, the same way, this difference divided by that one. So therefore next pair of points we try to get here y2 minus y1 divided by x2 minus x1. Okay, after that, here now, okay, this one is same as this term minus this one divided by here that difference. So that one will be put here, and this will be C2. Like that, we'll continue this, the divide difference table, and then the diagonal values become C0, C1, C2, and later on is C3, and so on. So to show this table construction, the computation, we did here some algebraic manipulations. Okay. Now we define officially divided differences. Zeros divided difference of function f with respect to xi is denoted by f xi, that is f of xi. Okay, so that this column, that is zeros divided difference terms. So for f value, we may use y here now. Okay, now the first divided difference of f, and with respect to xi and xi plus 1, is defined as that one. So that column is now, and for example, with respect to x0 and x1 can be made of that one. So that is now first divided difference with respect to x1 and x0. And now for each I, we can define. So in this table, we made this term, and then by using these two, also we got that term, right? Now, second divided difference with respect now 3 points is defined in this way, so that here x0, x1, x2, with respect to x0, x1, x2, the second divided difference is this one. That is, these two divided by that two value. So that is exactly this one. We recursively define the general case order divided difference with respect to xi to xi plus k here. And this bottom is same as that last point minus the first point, and top is here xi is missing here. Now for this term, now xi plus k, last term is missing. So in this way, by using the one lower degree divided differences, we can get here one higher degree divided difference values. Okay, that is official definition for divided differences. Okay, when you do that, then here the coefficients C0, C1, C2 are here the zeroth order divided difference with respect to x0, and C1 is now first divided difference with respect to x0, x1, and so on. In general, CK, the coefficients of kth order term, is now the kth divided difference with respect to x0 to xk. This is around the value. For example, here f kth derivative and divided by k factorial. Okay, so this almost derivative, kth derivative, and divided by k factorial. Okay, we'll see later on the meaning and how these divided difference are related with derivative terms. Okay. Okay, here we have Newton's divided difference table. In the beginning, that is x values, x0, x1, x2, x3. That is zeros divided difference. So at x, so that f of x0, f of x1, and so on. You may write down here y0, y1, y2, y3. Okay, now this is first divided differences. That is, this subtraction divided by that subtraction, this one. And this subtraction divided by that one is this one. And this subtraction divided by that one is here. Now for this second divided difference, here, these two subtraction divided by x2 minus x0. Now for this one, these two subtraction divided by now that one, x3 minus x1. This is second, so that you have to get a second point from here. Okay, now the third divided difference, that is these two difference divided by now jump 3 x0 to x3 to x0. So that is the bottom is x3 minus x0. Okay, and here this is a pseudocode for the construction of divided difference table. Okay, the input is xi, yi, so that for f array here, now this portion, that is, we save this one separately, and from this one, that's now f metric. Now this is f0, zeros column is including now y values, and here the loop is, okay, I is outer loop, so that, and I indicates the row, and j is column, so that the computation is done row-wise way. So here, j is moving from 1 to I, so that from 1 to I, that's now I is 1, so that only this one. Once I is 2, then 1 to 2, that is computed. And after that, now I is 3, then j is from 1 to 3, this will be computed. That is exactly, this formula is exactly the same as around here. So low-wise way, it is computed. Now, you can do it column-wise way. Also, in our hand computation, we'll do column-wise way. But in computer implementation, it's often row-wise. The reason is, now, after finishing this one more data point, for example, x4, y4 is given, then we put here, and we finish this one more row. Then that's it. So that the computation code is usually in row-wise computation happened. Okay. Okay. Let's try to get Newton interpolating polynomial for the data in this table. Okay, we'll try to use the technique. So here we start with x and y, which is zeroth divided difference anyway. Okay, we make it that way. Here x value is 0, 1, 2, 5, and y value is 1, minus 1, 3, and minus 189. Now we have to get dd1. Okay, that is this difference minus 2. Okay, so that minus 2 divided by that difference is 1. so that is minus 2. And the difference is 4 divided by 1, so it is 4. And the difference is the same as minus 192 divided by 3. So what is that? This is minus 64, right? Okay, so that is the DD1 column. And we'll go here, second divided differences. Okay, this difference is 6, and divided by here, jump 2, so that 2 minus 0, which is 2, so that is a 3. Okay, now this difference is a minus 68 divided by, now jump over there, so that is 4. So there is now minus 17. Okay, now we reach at the final one, DD3. The difference is minus 20, and jump 3 here, so that from here to there, that is now 5. 5 minus 0, 5 minus 0, which is 5, so that is minus 4. Now, we finished the constructing table, and this one is C0, C1, C2, C3. Okay, these are the coefficients of Newton interpolating polynomial. So that 1 minus 2, x minus x0. So this x coming from x minus x0, which is 0, so that there is x minus 0. That becomes x. And this 3 times x minus x0, x minus x1. x1 is 1 now. And here, and then finally, minus 4 times x minus x0, x minus x1, x minus x2. Okay, that's the final answer for the problem. Okay. Now we have here properties of divided differentials. Now, once f is a polynomial of degree k, then if you try to get here now the divided difference of degree n, so x0 to xn, then must be 0. It's a kind of a Cn. Now, if you are trying to get the nth order polynomial, then there is coefficients of the nth order term. Now, originally, the function f is polynomial of degree k, and n is larger than k, then the coefficients must be 0. Also, mathematically, we can prove that. Now, one question is that, what if we permute the points? Right now, it's ordered x0 to xn, but if we change the order so that now it becomes z0 to zn, but the same points, but different order, then the nth order, the divide difference are different. That can be a question. But here, fortunately, they are the same. Even though you permute the points, now if you're using all the points, the permitted points, then the corresponding divided difference must be the same. Okay. Now here, and error in Newton interpolation. Okay, here, P is the polynomial of degree n, and that is interpolating f at n plus 1 distinct points, x0 to xn. If t is a point, not the nodal points, then here at the point t, the difference is now can be given in this way. This divide difference times now t minus xi product. So here in the original interpolation error theorem, this portion, that one, that portion must be here f n plus 1 first derivative at some point evaluated divided by n plus 1 factorial, right? But here we can prove also that this divide difference is the same as that. Okay, here the proof is given. So here we can say that now for x0 to xn, the divided difference can be written as here. Now that one is, we have one more t here now, but we are including only from x0 to xn. The divided difference is same as 1 over n factorial and f nth derivative evaluated at some point psi. Here the proof is given, so that if you are interested in mathematics, then try to read the proof. So here the conclusion is that divided difference is a kind of derivative value scaled by n factorial. Okay, here that is a self-study. You can prove it here by using the divided difference formula, such one. So try to do it yourself. Okay, that's the end of section 2.2. Thank you.